Hi and welcome to CPS. I hope you all had a good week. If you like to use closed captions, you can turn them on at the bottom using the live transcript button. Today I have the honour of introducing Krystal Vasquez, who is a PhD candidate at Caltech studying atmospheric chemistry. As part of the Wimberg lab, she studies how air quality is impacted when urban pollution mixes with natural emissions from trees. Outside of her research, she translates scientific topics for a variety of audiences, in addition to highlighting how scientific discoveries and culture can impact marginalised groups. Krystal is an accomplished science journalist with pieces published in many outlets, including Scientific American, JSTOR Daily, and Chemistry World. Alongside research and writing, she also regularly advocates for the creation of more inclusive environments in both academia and STEM. So I'll hand over.
Awesome. Thank you so much for the introduction. So, as was just said, my name is Krystal, and my pronouns are she, her, hers. And I'm very honored to be here today. My talk will essentially be split into three parts. The first two parts will talk about an analytical technique I helped develop that has allowed us to better understand how air pollutants are formed in the atmosphere. And the third part will speak a little bit about my experiences as a disabled chemist and talk a bit about some of the reasons why disability continues to be underrepresented in STEM. So let's kind of start at the very beginning. One of the first things that we are taught when we learn about our atmosphere is that it's made up of 78% nitrogen, 21% oxygen, and 1% other. But I wouldn't let this 1% fool you. It turns out that this other category is actually an extremely important fraction of our atmosphere. Granted, it may not seem that way at first, especially considering that most of it is just made up of argon. But if you dig a little deeper, you'll find a multitude of other compounds there, such as greenhouse gases, which have long been known to impact our climate, and what I believe are a very underrepresented class of compounds, which are sometimes referred to as nonmethane hydrocarbons. And I say underappreciated because despite the fact that these individual compounds are only present at parts per billion levels, they are actually considered some of the major drivers of our air quality. So there are many ways that non-methane hydrocarbons can enter our atmosphere. Um, and they can be emitted by anthropogenic sources such as fossil fuel combustion and agriculture, as well as through natural or biogenic sources such as plants and wildfires. But regardless of where they originate from, when these hydrocarbons enter the atmosphere, they're essentially entering into what can be considered a low temperature combustion engine, which ends up oxidizing these hydrocarbons on the time scale of hours to days. In the daytime, this engine is fueled by this guy, the hydroxyl radical. And as a byproduct of this oxidation reaction, these hydrocarbons can end up producing air pollutants such as tropospheric ozone, which is not only a major contributor to photochemical smog, but it's also been known to, or it's also been associated with the development of a number of pulmonary and cardiovascular diseases when faced with prolonged exposure. But ozone isn't all they produce. They can also transform into a variety of compounds such as peroxides, nitrates, and carbonyls, just to name a few, all of which belong to a chemical family known as oxygenated volatile organic compounds. Now, the aforementioned functional groups can make OVOCs even more reactive than their hydrocarbon precursors, which means that they can also be oxidized in the atmosphere as well. So, similar to the hydrocarbons, further oxidation of the OVOCs can result in the formation of even more ozone, as well as even more OVOCs, some of which are air pollutants in their own right, such as formaldehyde. Alternatively, we can also continue to add functionality onto the existing OVOC structure, and this creates multifunctional compounds, which once formed, they can undergo several different pathways, two of which I'll highlight here. First, adding functional groups to the compound typically results in a lowered volatility, and these compounds can partition into the particle phase, which contributes to the formation of aerosols, which, similar to ozone, also contributes to smog and decreased visibility. and has a number of health impacts associated with them as well. Sometimes, however, these multifunctional OVOCs still have a high enough volatility to stay in the gas phase. And when this is the case, they can continue to react with OH or even other oxidants that are present in the air. And that essentially allows them to re-enter this oxidation cycle and create even more ozone and more OVOCs in this kind of self-perpetuating cycle. However, despite their importance in the atmosphere, OVOCs are really quite difficult to measure. And this is mainly due to their reactivity, the wide diversity of functional groups that are present in this chemical family, and the fact that many of them are present at even lower abundances than their non-methane hydrocarbon counterparts. And that's why existing techniques have historically focused on smaller, more abundant compounds, which, while important, can, which while still useful, also means that there are still a lot of uncertainties that we need to account for as we attempt to predict how concentrations of pollutants like ozone might change in response to, say, changes in air quality regulations. That, of course, doesn't mean we've been completely unsuccessful when it comes to balancing out the scale. In fact, there are kind of two main techniques that have become quite popular amongst atmospheric chemists when it comes to measuring this larger OVOC family. One of the most popular tools is chemical ionization mass spectrometry, or what we call CIMS. This is because the CIMS is able to measure these compounds using a soft ionization technique that ionizes the chosen analytes using a specific reagent gas. Mass spectrometry in general, it has a fairly low detection limit. And in the atmosphere, the CIMS has been shown to be capable of measuring atmospheric species down to parts per trillion levels, so quite tiny. Also, in comparison with some alternative mass spec techniques, like, say, electron impact mass spectrometry, this is a relatively gentle method of forming ions that really minimizes fragmentation, which is great for fragile compounds like OVOCs. It's also a pretty versatile method. There are multiple reagent ions that have been used by the CIMS, each of which is specialized with measuring different subsets of compounds. And there are a number that are currently available, which are capable of measuring OVOCs specifically. Of course, no instrument is perfect, and so the CIMS is only capable of separating compounds by mass. And this might not really seem like a big deal at first, but many OVOCs share the same chemical formula but only differ in functionality or structure. And these seemingly small changes in the structure can often end up impacting how these molecules behave in the atmosphere. For example, the molecule I'm showing on the left oxidizes in the gas phase and is actually the precursor to the molecule on the right, which contributes to aerosol formation. But since both have the same mass and chemical formula, to the CIMS, they look the same. It kind of makes sense then that we really want to start, if we really want to start unearthing OVOC chemistry, we need a technique that's able to tell compounds like these apart. And that's kind of one reason why gas chromatography, specifically GCMS, has grown quite popular, because unlike the CIMS, GCMS has the potential to separate compounds based on multiple chemical properties. So the GC can separate based on, say, polarity, and the mass spec can separate based on mass. The GC is also great because we don't have to worry too much about detection limits either, since gas chromatography can kind of get around this by allowing us to pre-concentrate the analytes on a trap that's typically located upstream of the column. Unfortunately, it also does have its downsides. For one, the GC is usually attached to an electron impact mass spectrometer, which, while it does provide some useful structural information that can distinguish isomers, like I said, it's a highly fragmentative process, and determining which fragmentation patterns result from which compounds is kind of a bit of headache. Also, OVOCs can be lost or converted into different species at different stages of the GC analysis. And so right off the bat, before it even enters the GC, many of the commonly used traps use solid adsorbents, which have been shown to convert many OVOCs into unwanted products and artifacts. There's also the fact that many commercial GCs are typically run above atmospheric pressure, which again, not great for fragile multifunctional compounds that are used to just hanging out in the atmosphere at, I don't know, 1 atmosphere, I guess. Um, but, it would really be nice if we can kind of take the best things from the CIMS and the best things about the GC and put them together, because this would make like the ultimate OVOC measuring tool. And it kind of turns out that we can enter the GC CIMS. So we've added a GC upstream of the CIMS that allows us to separate compounds by mass, but still also lets us distinguish between different structural isomers, much like a GCMS, but using a softer ionization technique. Of course, we've had to substantially modify the GC component in order to kind of get around all of those existing analytical challenges that I've mentioned previously. That's why this instrument uses a specialized non-commercial GC that actually operates below atmospheric pressure. And this is great for our OVOC analytes due to a couple of advantages it provides. Now, without getting too deep into chromatography theory, I can say that due to the lower pressure, this GC allows analytes to be separated on a shorter column. We use a 1 meter to a 4 meter usually, as well as allows compounds to be eluted faster and at lower temperatures. And all of these three things basically reduces the likelihood that a compound will fall apart before it's even detected. We also circumvent the use of an external trap, and we actually end up cryotrapping directly on the head of the column itself. And again, this just reduces the number of places where OVOCs can be lost or side reactions can occur. And it turns out that this is a powerful tool, though it may not quite seem like it from the figure I just popped up on screen. Shown here is a signal from the GC CIMS of an OVOC that it's sensitive to. It doesn't really seem that remarkable at first. You can see that this one compound peaks in the early morning and again peaks in the late afternoon. But now with the GC upstream, we can take snapshots of the signal and have a better idea of what's going on. So it turns out that in the early morning peak is made up of one component, which I show in the chromatogram in blue. And in the afternoon, it's an entirely different compound, which I show in pink. Of course, this is kind of just a proof of concept. Perhaps this would be a bit more impressive if I can even tell you what this compound is, or even what it does in the atmosphere. But the truth is that I actually don't know. This is just something really cool that I saw when I was looking at the data. But that's exactly why I'm going to switch gears and start talking about a specific case study in which we deployed the GC CIMS onto one of the rooftops of a Caltech campus building and used the data set obtained from this field study to help us better understand the atmospheric fate of atmospheric compounds such as ozone. But before I can get the ball rolling, I need to provide a little bit more background information, this time on the atmospheric chemistry of isoprene. So isoprene is an important biogenic compound emitted from trees and is one of the most abundant non-methane hydrocarbons in the atmosphere. Its two double bonds also means that it's really reactive, usually only lasting for a few hours. And the combination of this abundance and its reactivity means that it's really important to understand its chemistry because, as I'll show in a minute, it has the potential to influence a number of different air pollutants. So kind of like what I just went over, similar to many other hydrocarbons, isoprene is oxidized by OH and forms an isoprene peroxy radical. In places like LA County, which Caltech is a part of, RO2 reacts readily with nitric oxide, which is an anthropogenic pollutant, and it's notably produced from cars, which Los Angeles has quite a lot of. The next step in the reaction kind of branches into two main pathways. For context, the branching ratio that corresponds to this pathways is denoted by alpha, which is about 13%. The main reaction pathway, 1 minus alpha, produces nitrogen dioxide and some other species, but those aren't important right now. And this nitrogen dioxide can quickly photolyze to produce our old friend ozone, as well as nitric oxide, which can then end up reacting with yet another proxy radical, and it essentially initiates this ozone forming catalytic cycle. The other reaction pathway, alpha, is a bit more straightforward. It just produces a multifunctional OVOC called the isoprene hydroxynitrate. But despite this being a minor pathway, it's actually quite important because these hydroxynitrates end up acting as a reservoir for NO and NO2, which is collectively called NOx, which can completely bypass the catalytic cycle and forego the formation of ozone. There's a small caveat though, that isoprene nitrates can act as either a temporary or a permanent reservoir, depending on how this compound behaves in the atmosphere. And as we just learned, OVOCs can react in quite a number of different ways. Specifically for this compound, there are three main loss pathways that are thought to be important, which can be divided into those that cause the isoprene nitrate to act as a temporary reservoir and those that cause it to act as a permanent NOx sink. When isoprene is oxidized by OH, it has been shown to release NO2 back into the atmosphere after a couple generations of chemistry, recycling NOx into the atmosphere and producing ozone. It's important to note that in this scenario, it does take time for this chemistry to occur, and therefore both NO and ozone are now being formed downwind of pollution sources, which extends their reach. 1 second while I take a drink of water. Let's see. Alternatively, the isoprene nitrate can eventually be deposited onto surfaces. Most compounds end up doing this in the atmosphere eventually, and this essentially acts as a permanent sink that takes away the isoprene nitrate and NOx along with it. There's also many multifunctional compounds. The isoprene nitrate can partition into the aerosol phase, acting again as a permanent NOx sink. And as a bonus step, if there's enough water present in the aerosols, the isoprene nitrate can then hydrolyze, forming nitric acid, which is another air pollutant and a main component of acid rain. There we go. So which loss pathway is the most important? It seems like this would be a fairly straightforward question to answer, because really all you need to do is figure out the loss rates for these three different pathways and compare them to each other to see which one's the fastest. Unfortunately, it's not really that simple, and that's all because isoprene is an asymmetric molecule with two double bonds in which OH can add across either of them. Specifically in the atmosphere, OH can add to either the 1 or 4 positions, after which oxygen can add either beta or gamma to this OH group. And this means that the proxy radical is actually made up of several different isomers, 6 to be exact, the 4 shown on the screen, with the isomers to the rightmost side of the screen having both E and Z configurations. So suddenly our little problem got just a lot more complicated. Isoprene produces some distribution of these proxy radicals, and the distribution ends up being dependent on the amount of time it takes for them to react with other molecules like NO. And then after accounting for any additional chemistry these proxy radicals might undergo, we form some corresponding distribution of the isoprene peroxynitrates. I'm showing what the distribution might look like in an urban environment like Caltech. We can simplify this a little bit. 4 of the 6 isomers are present in such small amounts that their chemistry is pretty negligible in the grand scheme of things, but we still are left with a fairly complicated problem. And that is, to recap, that the isoprene nitrates are a reactive multifunctional OVOC that exists as 6 structural isomers of each other. The 2 most abundant are actually only present at less than 100 ppt if you sum up their concentrations. And as just a nice little bonus, there's no pure standards of the 1,2-hydroxynitrate, which kind of limits how deeply we can dive into this chemistry in the lab. Altogether, these 4 properties have hindered isomer-specific observations of the isoprene nitrate chemistry. And that's kind of a big deal. Why? because when we are modeling atmospheric concentrations of pollutants such as ozone, it ends up being highly dependent on whether these models treat these compounds as temporary or permanent sinks. If treated as a permanent sink, a model would predict that areas with lots of isoprene should produce lots of ozone. Whereas if it's treated as a permanent sink, it does just the opposite. But to determine which one's the right answer, we need to obtain direct observations of the chemistry that they undergo in the atmosphere. And this is kind of where the GC-CIMS comes in. GC-CIMS comes in. With the GC-CIMS, we're actually able to see 5 of the 6 isomers. Most importantly, we see the 2 most abundant isomers shown in the chromatogram in red and blue. I want to note that previous attempts to measure and separate out these isomers has resulted in the 1,2-nitrate, the most abundant isomer, to be lost before it's even detected. And that's not really great since it makes up more than half of the concentration of these compounds. If we can collect enough of these GC snapshots, we can now observe how these concentrations change over time. And we can also see how they change relative to each other, which is key to kind of uncovering how their loss processes may differ. So previous studies that have used both the GC-CIMS as well as other methods have already given us some insight into 2 of the 3 different pathways this compound can take. We know that deposition isn't that big of a deal because its atmospheric lifetime is about 24 hours. Oxidation through OH, on the other hand, which again, remember, gives us back ozone and NOx, is actually quite important. The lifetime at Caltech is approximately 3 hours and 2 hours, respectively. That just leaves the outstanding question of aerosol uptake and hydrolysis. We've used synthesized standards of the 4,3 nitrate, and prior research has shown that it's pretty negligible in the atmosphere. However, we don't know if that's the same case for the 1,2 nitrate, as no standards exist. But when we look at compounds that are very similar in structure in the atmosphere, we get the idea that this loss rate might actually be quite fast, but how fast and can it outcompete OH oxidation is still yet to be seen. So we can take the GC-CIMS and take it to the lab and get a little bit more insight into this hydrolysis loss. This is kind of what a typical lab setup looks like. To a giant Teflon bag, we add isoprene, an OH precursor, NO, and for this particular set of experiments, humidified air. And then we can turn on UV lights for long enough to form OH and react a small fraction of the isoprene, giving us the isoprene nitrates. We then turn off the lights to stop the chemistry and kind of monitor how these nitrates decay over time with the GC-CIMS. What we found was something quite peculiar. So in this setup, there should be nothing in the bag right now that's reacting with these nitrates, but we're still seeing that the 1,2 nitrate is decaying quite fast, especially compared to the 4,3 nitrate counterpart. And its lifetime happened to be pretty dependent on humidity levels. At 50% RH, we saw a 45-minute lifetime, and we observed a 15-minute lifetime at 85% RH. Unfortunately, though, with this setup, we're not able to obtain quantitative data, aside from saying that hydrolysis could be happening, and if it is, it's quite fast. And this is just because the reactions were probably occurring on the chamber wall or the bag wall, which kind of became hygroscopic over time because it's just prone to having a lot of different experiments that like to deposit like sulfate ions and stuff on the walls. So we had to seek other methods. Just a quick aside, I keep kind of mentioning hydrolysis, but what information do we actually need in order to determine the loss rate? First, when the gas phase hydroxynitrate enters the particle, the amount that can enter this particle is determined by its Henry's law constant, and that's denoted by Kh. And once in the particle, it can hydrolyze with a first order loss rate, Kaq, and neither this rate nor the Henry's law constant is known for the 1,2 nitrate. We did finally, after many years, finally get or we're finally able to successfully synthesize a 1,2-nitrate standard. However, it is quite impure, and so it does still limit what we can do with it. I'm showing the NMR for this standard on the screen. However, let's see. Where was I? So we tried to use the standard to attempt to measure the Henry's law constant of this particular isomer, but that failed because it was a bit too reactive and there was too large of an uncertainty that ended up in the experiments. We are able to get the Henry's law constant for the 4,3-nitrate, which we also synthesized, which I've shown here on the screen. Since these two isomers probably don't behave that differently when they're entering the particle, we can kind of assume that that this is the lower limit of the Henry's law constant for the 1,2-nitrate, and then the upper limit we just base on some very similar molecules that are also formed when isoprene reacts with HO2 instead of NO. For the hydrolysis rate, methods have already been published in the literature, and it uses proton NMR to investigate the hydrolysis kinetics in deuterated water. This is a method that has already been used for the 4,3-nitrate, which is, again, why I was able to say that it was negligible in the atmosphere. But when we tried to do the same thing with the 1,2-nitrate, when we added the mixture of the 1,2 into the deuterated water and then just reinserted it really quickly back into the NMR, there was virtually no sample or no evidence of the isoprene nitrate left when we took a spectrum. But we can kind of make a few assumptions. They're not the greatest, but they're assumptions. Based on the NMR signal and also the ratio of the 1,2-nitrate compared to the other impurities that are also present in this mixture. And we can place a lower limit of a rate of 0.1 per second, which is extremely fast, especially compared to the 4,3-nitrate, and pretty much kind of explains what we were seeing in the chamber bag. But the thing about the lab is that sometimes compounds behave differently than they do in the actual atmosphere, or sometimes they behave differently in the lab than they do in the actual atmosphere. And so it would be really nice if we could kind of have evidence that this is actually happening. And that's exactly why we deployed the GC onto the Caltech campus. I'm showing the building here that it was on, as well as just some example data. So at Caltech, we were able to obtain a diurnal average of how the two isomers changed relative to one another. And we can right off the bat kind of perform a sanity check and see if deposition and OH oxidation can explain the pattern we're seeing. And it turns out that it doesn't at all. In fact, it kind of gives you the exact opposite shape of the graph that is shown here. And what's particularly interesting is that in the afternoon, it seems to increase a bit, and in the whereas for the real signal, it decreases over time. And we can see why this is happening when we look at the GCs themselves. Just like in the lab, the 1,2-nitrate is decreasing at a substantially faster rate than the 4,3-nitrate. And this kind of gives us the evidence we need to say that, okay, hydrolysis might actually be happening here. So since we have a little bit of evidence, we can start modeling hydrolysis in an atmospheric model. We can just change the rate until it starts corresponding with the signals that we saw. And based on this, on the NMR, we saw that it was greater than 0.1 per second. And then based on the model, we can constrain it even further to 25 to 250 per second. And again, this is extremely fast, especially compared to the other isomer. We can then use these numbers to kind of back calculate what the atmospheric lifetime should be. And we get a range of 4 to 7 hours, with the shorter lifetimes being present in the later afternoon, evening, where relative humidity is increasing over the night. It doesn't quite outcompete OH oxidation at Caltech, but it's still substantially fast enough that it does make a difference. And in fact, even at the longer lifetimes, it's still taking up over a third of the 1,2-hydroxynitrate loss. And so this is implying that these compounds as a whole act as the permanent NOx sink. There's also the matter that Caltech, again, is in an urban area, and urban areas tend to have a lot more OH than typical, like, surrounding more pristine environments. And so OH oxidation rates are actually a lot longer elsewhere, going from 9 to 6 hours in the typical atmosphere. And this is definitely a lot longer than it would take for a hydrolysis to occur. And then California, specifically Southern California, is pretty dry and arid. And so there's actually not a lot of water vapor in the air itself. And so this is probably a lower limit of what the hydrolysis rate could be. In other places like the Eastern US or other places in the world, relative humidity is a lot higher. And so the lifetime could actually be quite shorter. And so basically, what this all sums up to is that the isoprene nitrates actually act as a permanent sink of NOx for the most part. And this means that areas with a lot of isoprene probably are taking up a lot, or probably have a lot less ozone than we would otherwise predict. And when we actually model this, we can see that these models better match the observations than they did previously. So that kind of concludes the science portion of this talk. And so we're going to switch gears a little bit, to, or I guess a lot, to talk about disability. As a scientist, I do like numbers, so we're going to start with a little bit of statistics. And for the record, I'm using numbers specifically for the UK, hence my audience. But these findings are actually quite universal across the US and Canada as well. So disabled people are underrepresented in science. That's just kind of plain and simple. Even though 19% of the working age population is disabled in the UK, they only make less than 12% of the student population across all physical science disciplines. And this percentage drops off dramatically as you start going through the academic ladder. And so I'm showing the statistics here for chemistry, physics, and earth science. And we go down from 12% in the student population to less than 2% of professors. And this, quite frankly, is kind of disturbing, and it goes far beyond a leaky pipeline problem. Disabled people are not only less likely to not pursue STEM as an education, but they also end up leaving these fields at an unprecedented rate. And if we're being honest with ourselves, this is a pretty overlooked problem, and very little has actually been done to try and even improve these statistics in the first place. Over the past 12 years or so, there's only been a 1.8% increase in the number of disabled academic staff in STEM. And oftentimes, when they do manage to make it into these positions, they tend to end up they tend to make up a slightly higher percentage of part-time staff than they do full-time staff. Now, admittedly, in some cases, this could actually be because part-time is a lot more suitable for their needs. But I think it's safe to say that some of it is also partially stigma, discrimination, and microaggressions, which all come into play. Something I also find quite interesting while preparing for this talk is that I'm kind of an anomaly. Disabled academics are actually less likely to be found doing research, with a higher percentage found in teaching-only positions rather than the alternatives. And this is kind of a nice segue to a piece I wrote for Chemistry World back in, I believe, December, where I talked exclusively about this issue from the perspective of inaccessible chemistry labs. So we might not realize it, but we've kind of made STEM and academia into an environment where able-bodiedness is the default. And our labs perfectly reflect this. If you think for a minute, how easy would it be for someone in a wheelchair or someone who is blind to navigate your lab spaces, either teaching labs or research labs? How about someone with sensory processing issues, which is something that I deal with? I know for a fact that my lab is extremely loud thanks to the hum of the vacuum pumps and extremely bright thanks to the fluorescence. I've definitely left lab several times with a migraine and not just because of a failed experiment. And some might argue that labs have to be built in compliance with equity laws. And in the US, that would be the ADA. But the ADA and the equivalent in the UK is kind of just the bare minimum. And sometimes the modifications can be useless for the people who are actually in the lab. For example, most of these guidance and requirements kind of just focus on wheelchair users. It's kind of like what you think about when you think of disabled. You think of the disability placard wheelchair sign. And that kind of shows up in my lab. For example, we have wheelchair accessible workbenches, but a lot of my work is actually spent standing in front of an instrument or standing in front of a fume hood that doesn't even let me sit down properly in a chair. Um, we have to consider that laboratory experiences are crucial for the success of all scientists and engineers. All students eventually need to take a lab course at some point in their education. And so it's no wonder that there's such a sharp drop off as you move through the academic pipeline. And also, it's important to remember that disability can happen at any time. It's a pretty natural part of life. It happens as we age. And sometimes, if you're me, it happens in your mid 20s. I wouldn't recommend it, but it's just how life is sometimes. And so we need to find ways that not only stop people who are already disabled from entering STEM, but making sure that people who become disabled no longer leave STEM. One solution is universal design. And this is a method that purposely designs a space so that it's usable by the majority of people, regardless of disability status or other characteristics. It's important to note that universal design will never really negate the need for accommodations, but it does proactively incorporate some of the most common ones so that there are more resources to go around for people who have additional needs. Some examples I talk about in my piece are adjustable height fume hoods, which can accommodate wheelchair users or those like me who can't stand for long periods of time. There's also automatic doors or ergonomic tools for people who struggle with grip strength, and pull cord alarms for people who are closer to the floor. And this one is particularly important because many safety features like safety showers actually aren't quite accessible, and that can actually mean life or death for a disabled scientist. Now, of course, the question is kind of, this is all great, but how do you even fund this? And I don't actually have a good answer. I don't know that many grants that are set aside for doing something like lab renovations. And lab renovations in general are a big deal because you want to get research done. And even the grants that are specifically for diversity often leave out disability from things that they possibly fund. But that doesn't mean that we can't call for change and call for these funding agencies to start including disability also. And it means that we can also start asking our universities to help set aside funds for these lab renovations, or at least to make sure that new labs are properly suited for to welcome disabled chemists. Of course, lab accessibility is kind of just the tip of the iceberg. There are plenty of different additional barriers as well. For example, I've never, to my knowledge, had a disabled professor. And as far as I know, there are no disabled professors in my department. And if they are, they don't feel comfortable enough telling anyone. So, because of this, there's a substantial lack of mentors and role models. And so, when I became disabled, there was no one I could really go to ask how to navigate this whole new life that I was living. And there's also a lot of difficulty obtaining necessary accommodations. While it kind of skirts on the barrier of legal and unlegal, universities do put up as many roadblocks as they can to prevent disabled students and staff from obtaining the necessary accommodations. I don't know why it happens, it just happens, and it's the reality that many of us face. Not to mention that when you actually become disabled during your education, there's no resources in place to help someone understand what accommodations are available or what they might need with their specific circumstances. And then third, there's just the general culture of academic research and scientific research. There's a lot of emphasis on long work hours and research input and productivity. And there's been a lot of talk about how this is toxic in general, but it also specifically excludes those with certain disabilities, including energy limiting conditions, such as something that I have. And then, of course, there's just stigma, discrimination, microaggressions, all of which discourages disabled folks from either pursuing a STEM education in the first place or forces them to leave at some point in their career. In fact, I'm going to be one of those people. When I graduate in however many months, I've made the decision that I'm no longer going to pursue research as a career. And I don't want to imply it's because that my disability has made it impossible or because I can't hack it. And this isn't kind of a cry for sympathy either. I think that I'm just as good of a scientist as I was before I was disabled. And the fact that I made it to my end of my PhD, well, almost, is a feat in and of itself. But with all the statistics that I showed you earlier, you can kind of start thinking of them as just numbers after a while. And I hope that for those of you attending this talk, I can act as one concrete example to show why including disability is so important. But yes, I am leaving science, and that's basically because of the stigma that I've kind of briefly touched on earlier. People assume that I can't do things or have assumed that I can do things, but on the same time scaled as an able bodied colleague. And it's just not really worth the emotional labor anymore to keep fighting this kind of stuff. But that said, that doesn't mean I'm not gonna, I'm just gonna suddenly stop advocating for a more inclusive STEM environment. We need a place where disabled folks can be welcomed. After all, disability is diversity. And just like other forms of diversity, like race, gender, and sexuality, all of which I represent, science will always be better for excluding it rather than excluding it. And so that pretty much concludes my talk. Really quickly, before we open up for questions and such, I just want to acknowledge my colleagues and my lab mates and my co-authors, which are shown here, all of which basically made the science that I talked about earlier happen. I would also like to acknowledge Caltech and the staff, which helped me set up my field experiment, and just acknowledge that the funding for all of this research came from the NSF. I want to thank you all for listening. If you do want to reach me after this talk is over, I've put my contact information on the bottom of the screen. And I guess I'll happily take any questions. Thanks.
Thank you so much for an absolutely incredible talk. We really appreciate your insight into both underrepresentation of disabled people in STEM careers and your research that is so important. I've loved hearing about it. We can now have any questions if you'd like to type them into the chat or if you'd like to unmute yourself. We have a question from Susan, who asks whether the column in the GC CIMS needs to be cleaned and if that's a problem.
It's not particularly a problem. We just heat up at the end of a GC cycle, we heat up the column to a high enough temperature where everything's either going to be destroyed or just cleaned out in like a big flush of crap, I guess, for lack of a better word. And so we do need to replace it every so often because GCs do degrade, but that's not too big of a deal.
Okay, thank you. I have a question. You mentioned that funding is a big problem for renovating labs or for properly helping disabled staff and students. What do you think is the most important thing that current departments can do that perhaps doesn't need funding to help support students?
I don't know. Money is always a big issue in science in general.
Yeah.
I think just probably one thing that can be done straight from the get-go is when a PI takes a new student into a lab, or when they're starting a teaching lab, perhaps they can just make an open environment that makes students feel welcome to talk about any accommodations. Not necessarily giving them any like personal information or anything like that, but just saying like, everyone's going to have different needs. Everyone has a different like body and mind. And so if you ever need anything, please don't hesitate to come to me and we can make it work. And nothing about what you disclose will be, you know, talked about like with the broader classroom either. And so, yeah, just making an open environment, making sure that people know that it's okay and needing accommodations isn't anything that they should fault themselves with, I guess. Yeah.
Miranda asks, what would you like to see happen in the next 5 years in this field to build on what you've achieved?
I would like to see basically the GC CIMS is a great instrument. It can use a little work. It is a little bit slow when it comes to measuring, because it takes like about, maybe I didn't mention this, but like 20 minutes to elute a compound. And if you're doing something like some other research I do is you fly in a plane and you measure compounds as you're flying through, but you can't really do that with this particular GC setup. So finding out a way to maybe do like tandem GCs, find a way to use different columns to see different see different compounds, and then just get this a more popular instrument. It has been used with different CIMS than the one that I particularly use, and that has given us a little bit of insight into like the types of compounds that are emitted by fires. So I think there's a lot to go on. I think this is just a starting point.
Thanks very much. That's really exciting. Tina Maria says, thank you very much for an inspiring talk in both parts. She's wondering whether the OVC might be beneficial to the atmosphere in some way.
Um, I mean, I don't know if they would be necessarily beneficial, but not all of them necessarily create pollutants. Um, some of them just kind of hang out. I think it just depends. Like some OVOCs are just natural. They are formed usually from plants as like a stress response. And so they're always going to be there. And so I wouldn't say that they're inherently harmful, but I will say that when mixing with, I don't know, like NOx from car tailpipes or factories, then that's when it can get a little more hazardous for us as humans.
And a final question, I'm not really sure how to word this, but when you're mitigating the effects of these pollutants, do you have to have a very different approach, perhaps for an urban environment instead of a rural environment?
Yeah, so one of the main components that determines this is this NOx compound that I keep talking about. And it, in urban environments, it's the one that's basically reacting with all these hydrocarbons and VOCs. And you can reduce NOx to a certain point to reduce the ozone it produces. But at a certain point, if you reduce it too much, it actually ends up producing other things like aerosols. And so there's kind of this fine balance you have to meet. And that's kind of why it's so important to really get this chemistry down, because if you can kind of tell what's creating ozone and how it changes when you change different things, then you can say, okay, if you reduce like car emissions by 50%, you'll get um, better air quality. But if you reduce it any lower, it's not really worth it. Like that kind of thing. It's a balancing act, essentially.
Thanks very much. I'd like to say a massive thank you from the whole society for your talk. We're very grateful for you coming to speak. And there's been some lovely comments in the chat saying that we all hope that there's going to be a much more accepting environment for STEM in the future.
Yes,
So thank
I
you very
certainly
much.
hope so. Thank you.